All right, we're going to go over exponential functions. Now, an exponential function has two distinct looks to it. We have what's known as, whoa, that wasn't very well done, hold on, as exponential growth, and we have something that's known as exponential decay. Now, exponential growth and decay both will never cross our x-axis for what we're doing. Okay, it's called an asymptote. So it's something that it'll never touch. It'll get closer and closer and closer, but never touch it. Think about like walking halfway to something. So they say this is happy me. Here I am. Okay. And I decide to walk halfway to this wall. Okay, so I'm going to walk halfway. I'm not at the wall yet. If I walk halfway again, I'm not at the wall. If I walk halfway again, I'm not at the wall. So if I continue to walk halfway, I never end up making it to the wall. Okay? So this is like an asymptote. It'll never touch this x-axis. And that's one of the characteristics on a graph we can use. The other one that it essentially increases in an exponential way. Now this part of the graph could look very similar to a quadratic relationship. So we have to be very careful. If we're only seeing something like this, we're definitely going to have to acquire more information in order to figure out if it's quadratic or exponential. So let's go down, and let's say I've collected a bit of data. I want to figure out if I have a linear, a quadratic, or an exponential relationship, or maybe none of the above. So the first thing we do for linear is what? First differences. So let's quickly do first differences. 100 subtract 80. Let's try to do it with 20. 80 subtract 64. 16. Here's a tough one. 64 subtract 51.2. What is it? 13.8. Oh, you guys are quite good at that. Good. Is this a linear relationship? No, our first differences are not the same, so that is not linear. Let's go to second differences. 20 subtract 16. 4. 16 subtract 2.2. Good. Is second differences, are they the same? No. So we're not linear or quadratic. Now, in order to find out if we're exponential, okay, exponential is a ratio. Okay, so we take the ratio of these values. We follow the same pattern where we take the number on the bottom and we divide by the number above it. So ratio has to do with division. Okay, it's not differences. Ratios are division. So we take 180. Okay, so I'm going to rewrite them so you can see this part. Just the y part of the equation. 80, 64, and 51.2. So we take this ratio. This becomes 100 divided by 80. Okay, we'll take a calculator out to find this ratio. 100 divided by 80, 1.25. Okay. Then we do the next pair. We take 80 divided by 64 and find our ratio. 80 divide 64, 1.25. And then finally, where is it now? 64 divided by 51.2. And again, we get 1.25. So this relationship is known as an exponential relationship. Okay? And this would be, because our ratios are positive, it would be growth. We're looking at exponential growth. And we can kind of make sense of that by looking at it. Right? If we take a look at this, our zero value was 51.2, and then 1 was 64, 2 was 80, 3 was 100. It was increasing. I know I drew an arrow downwards there, but the idea is it was increasing. So if we were to plot these, and this is probably not the best graph for it, maybe if I make these all 10s, okay? And we try to plot these values, we can see maybe exponential growth, 0 and 51.2. Okay, so 51.2 is about there. 1 and 64. 1 and 64. I think it was 2 and 80 and 3 and 100. 2 and 80. 3 and 100. So we're getting this type of movement. We know it's curved. And again, by just looking at the graph, we don't know if this is quadratic. So we took our ratios below to figure out that this is actually an exponential relationship. Now, an exponential relationship is usually written with something like this: y equals a b to the power of x. And anytime our variable is x, okay, this is an exponential relationship. So we'll have two values that will go into our a and our b in this case. Okay, so I can show you a couple examples, and we'll talk about how we can technically build that equation from the information we already have. If I were to show you y equals 2x, okay, when x is 0, so y equals 2 to the power of 0, what does y equal? What is an exponent to 0? We went through this already.
1.
Yeah, it's equal to 1. Okay, so at that point of the graph, we would have a value of 1. And almost as long as our a value is 1, all of our exponential relationships, when put to x as 0, our y-intercept will be 1, unless a is a different value. Depending on what that a value is technically our y-intercept. Okay? What is our y-intercept in the equation we've just done? 51.2. So from the equation we just had, we know that a is equal to 51.2. Just by looking at the graph and figure out when x is 0, that gives us a y-intercept, the a value. Our growth rate is our b value, so how much we're increasing by, or technically decreasing by. And in this case, we found that out with our ratio. What was our ratio? 1.25. 1.25 is technically our b value. 1.25. So if I were to build an exponential equation for this over here, we would say that y is equal to our a value, which is 51.2, multiplied by our b value, which is 1.25 to the power of x. Okay? I know we don't really have to build too much in this course. You might only have one small question for it, but it's relatively simple once we've done the ratios. Right? As long as we can figure out what the x-intercept is, that's our a value, and our ratio is our b value, it becomes very simple to build an exponential equation. So, our characteristics that we look for. If on a graph we have some type of asymptote, we know it's exponential. If our growth all of a sudden seems to take off very quickly, it can appear exponential, but we'll probably have to do a little more digging to figure it out. The main way for us to tell is by taking our data and finding the ratio of the y's. If our ratios are all the same, then we know we have an exponential relationship. Okay? If we were to just look at the equation, whenever the exponent is x, so a variable, we have an exponential equation. All right. Population growth. So we're going to talk about how this is an exponential relationship. We found an estimate online. We have no idea if it's really reputable. But anyways, they gave us an estimate of the world's growth rate to be 1.14%. Okay? So its growth rate is 1.14%. And our current population is, we think, around here. This is also what that site said. That could be incorrect. So if we were to build this, and I'm not going to ask you to build this, but I'm going to show you how this helps us use projections, exponential. The equation of this would be our population of the Earth is equal to, and this is billion, so technically 100 million. This is this number written out. That's how many people there are on Earth right now. And our growth rate would be 1.0114. Okay, this is where the 1.14, I turned it into a decimal by dividing by 100, so it becomes 0.0114. Okay, and that's how I got this part after the 1. And because it's a growth rate, I put a 1 there, not as important. But x, giving us our exponential equation. X is going to represent the number of years from 2013. So if we wanted to figure this out, what would be a year you guys would like to figure out?
Now.
2047, 1997.
2047.
First year.
Let's go like that.
2047?
2047. Now, what value would we put in for x? Well, we wouldn't put in 2047 because what's the year we're starting from? right? So year 0 is this year, right now. So we have to figure out the difference between these 2 years. So 2013, subtract this, and that's how many years have passed. Okay, so we have 4, 3. So we're looking for 34 years down the road. So we plug in 34 for our x. So the world's population at this rate is estimated to be 1.0114 to the power of 34. So let's take out a calculator, and this is an exponential relationship because it continues to grow and grow and grow. So assuming this growth rate stays the same through all those years, we take 1.0114 to the power of 34. And then I multiply this by my 7 billion. 7,160,000,000. 2, 3, 4, 5, 6. And our new number is estimated to be... Did I calculate that incorrectly? Yeah, 10 billion. So if this rate stays up, we're looking at about 10.5. I rounded this a little, okay? Billion people on Earth, assuming that this ends up being the growth rate over that time. And that's an exponential relationship. So for every year, our percentage tacks on more, very much like compound interest. Population is another way we use exponential functions.